Hello everybody, and welcome to Debugging Direct3D in your app. I guess the schedule's been pushed back a little bit, so we're starting a little bit later. So last month, I celebrated my 21st year at Microsoft, and so I'm so glad there's a party tonight. I'm going to be celebrating. For the last 9 years, I've been working in the graphics team, and I've been working on Direct3D, graphics drivers, and even some OpenGL at times. And for the last year, I focused on tooling and how you deal with debugging and analyzing your graphics. And so when I was given this opportunity to do this talk, I got really excited because I said, okay, I can do some really interesting things here. So but then I immediately turned around and said, wait a second, this is going to be a hard sort of talk to do because it's usually when you do a presentation, you're going to take some feature and you're going to talk about it, have lots of slides, and then you'll have maybe a short little demo about that feature. Well, I'm talking about debugging and how do you analyze graphics, which is more of a scenario. In fact, what I'm going to be doing in this presentation is doing mostly demo and only a few slides. So you'll find this is a sort of different type of presentation than you're typically have seen at these conferences. And what I'm going to try and do is, or what I will do is I will address some of the most common feedback we get from our developers is, okay, what tools do I use? Where do I get better tools? How do I do things? And so when I went to start preparing for this talk about a month ago, I went on a sort of quest. And I went to talk to our Direct3D developers. I went to talk to our graphics folks, the Xbox folks, the Windows Phone folks. I talked to our evangelists. And I asked them, okay, so what sort of things do both experienced and people who are new to Direct3D, what sort of problems do they run into? What are the common things that they have? And I got a lot of good feedback. In fact, I got so much feedback that I think I could probably put a talk together in the last 2 days. So I had to go through and really weed out a whole bunch of stuff. So I may wind up going a little fast, and I may wind up running over time, so I may have to cut it at the end. However, the demos I'm going to be using will be posting later on after the conference, and you can look at the various demos. Right. Now, so when I started looking at this, I said, okay, what am I going to use for a demo? Visual Studio ships with a bunch of templates, and they're fairly good starting points for building an application that's going to use DirectX. But in many ways, they're a little too simple. So I needed something that was more robust and so on. And so I looked at some of the applications we provided as samples for Windows 8, and one of them was the Marble Maze sample. And let me just bring that one up. It's the Marble Maze sample. You may recognize it. It's sort of a little game, and we can so this is the Windows 8 version of the sample, and I thought, perfect, this is a great example. I will start with this application, and we will port it to Windows 8.1, and everything will be happy, right? Now, like with any sort of project like this, as soon as a new developer gets involved, they start thinking, okay, there's a bunch of things I don't like about this program. There's some things I have to do as I go convert to 8.1, and then there's a whole bunch of other things because I want to restructure the code, I want to remove certain classes, I want to change the style of the coding. And so, a really short, quick conversion process turned into a several-week process as we did all these changes. And of course, how many people in here, when they do such a major code restructuring, write perfect code? I want to see anybody here. Oh, yeah, okay, we have one person in here who writes perfect code. So as part of the restructuring, I actually removed a math library from this application because it uses two. It uses a DirectX math library, or the Direct math library, and it uses this thing called Basic Math, which we used in Windows 8. So I standardized on one of them. And as part of that process, what happened is the little marble that you just saw, I got the math wrong. I basically wound up transforming it into an infinitely large flat plane that was spinning at a super huge rate. And so when I finally got the app running, I have this white background. I'm wondering, where did that come from? So anyway, it's very easy to introduce these sort of little logic errors, little coding errors, and we'll be looking at some of those. So let me just look at some of the things we changed. Well, luckily, a lot of the stuff from converting from 8.0 to 8.1 is fairly easy. Visual Studio will do most of the conversion that's necessary with the project file for you. For this sample, what I also did was took the sample itself and moved it on top of the new template that's in Visual Studio, the new DX template, which I actually like better than the way we did it in Windows 8 because it uses containment rather than inheritance. So you wind up getting a much cleaner breakup of your code. You have the DX rendering in one place, you have the game logic in another place, and so it's a little bit easier to follow. There's also style changes that I wanted to do, things like the Windows 8 sample used a lot of ref classes, and if you're not actually interfacing with the WinRT APIs, C++ app doesn't really need ref classes, so I wanted to just use normal classes, which also introduced bugs because ref classes initialize all the memory to 0, and when you change them to non-ref classes, now all of a sudden I had all these uninitialized variables that I had to go track down. So there are a bunch of things that happened. I removed a bunch of unnecessary files, like I said, the math library thing. Oh, I also wanted to annotate the code so that the tools I'm going to be demonstrating will be more meaningful and easier to understand. So we did that. And had to do this all in a couple weeks while working full-time at Microsoft trying to ship code for this conference. It's an easy thing, right? Nobody needs to eat and sleep. Well, luckily, I got some help on this. We had an intern, Lawrence Murphy, who came and did most of the coding for me. He did a really good job, except for he was still changing the code just before this presentation. So I'm hoping, it makes me a little nervous when he does that. So let's look at what we're going to do today. So I said this was sort of like taking a whole development cycle and breaking it down into an hour presentation. I've structured it as 3 separate demos. The first one will be focused more on, how do you prevent some of the common errors? How do you catch them? What do you do there? Once you get the app sort of running and it seems, decent, how do you actually debug the graphics? Because one of the things you'll notice with, any application that gets this level of complexity is there's the graphics calls, there's the logic calls, there's the other things, other goo that's necessary to just make the app work. And it's hard to really trace through it. You spend a lot of time in the debugger. And we have some tools that make it really easy for you to focus just on the graphics part, and I'll be showing that. And then the last part is we want to validate the application. We want to make sure that everybody who uses it works really, like it just works for them. And so I'll show you some of the tools that are available there too. Now, there's a bunch of documentation on MSDN. I'm mainly putting this slide up so that you can go look up some of that afterwards because I can't cover all these tools in detail. I'll be talking about the debug layers. What the debug layers is, you can think of D3D as actually being built in layers. There's the runtime, which actually does all the heavy lifting and work. And then on top of that, we have this layer that's installed with Visual Studio and the Windows SDK that does all the validation that, like you pass bad parameters or you go out of range. And it'll tell you when you do things, when you abuse the API. And it's all the sort of stuff you would want while you're writing your application, but you wish wasn't there in your retail code because it's going to slow it down, right? Because D3D is all about getting right to the metal as quickly as possible, so it's thin and so on. Now, the debug layer will catch all sorts of things. Not just bad parameters. For example, let's say the map call. I pass a null parameter on the map call. That results in undefined behavior, according to the D3D spec. Well, undefined behavior is actually a euphemism for, the application is going to crash. You maybe crash the operating system when you do that. Or, some terrible thing is going to happen that brings about an apocalypse in your code. So these sort of things it'll catch, it'll warn you, and you'll immediately know. There's some other things like copy sub-resource region is a very useful API for copying regular chunks of graphics memory around. But if you get it outside the bounds and you actually do the copy with the runtime without the debug layer, you may actually copy memory some random place and have really bad things happen. Again, undefined behavior. So these are the things that the debug layers are for. There's a control panel that I'll be showing that lets you tweak and manage what those debug layers will present to you and how it works. I'll be showing a little bit about how do you annotate your code so that the information the tools provide for you is more meaningful and more actionable very quickly. Things like naming the resources, tracing your code, and I'll show how that works. The Warp is you can think of as a software GPU that ships with Windows. And if you've been to any of the other talks earlier today or yesterday, we've been showing demonstrations of things like tiled resources. How do you actually build how do you build an application that uses these features before the hardware actually has that? Well, that's where Warp comes in. Warp, we implement all these features ahead of time, and even if your hardware doesn't have the feature, Warp will have it, and you can actually run on this software GPU, get your code working, and then when you do have the hardware support, you can actually then do it. The other thing that Warp is really good for, especially in the debugging area, and especially at this point in the project where we have a new OS, we have new drivers, we have new code that you're porting, and it's really hard to tell, okay, where's the bug? Is it mine? Is it somebody else's? Is it Microsoft's? Is it the vendor's? If you run your code with Warp, you can very quickly figure out, okay, it's in the driver, or it's in my code, or it's Microsoft thing, and you can figure that one out. And the last thing I'll be doing, and I'll spend a lot of time during the presentation, is talking about Visual Studio Graphics debugging. Now, this feature is actually in Visual Studio 2012, and we've done a fair amount of work with the Visual Studio team to make improvements and so on. And what it will do is let you actually take a trace of your application while it's running, get the individual graphics calls, and I'll be showing you how you walk through that and use that. All right. So with that, let's look at preventing some common bugs. I'm going to sort of play the mad scientist role here as I sort of hide half behind the podium and come out and try and talk to the audience. What I have... Right. So here is the converted program that we've converted. And what I'm going to do is just simply run this. And this was my first experience after we had done the port. I get an exception. Okay, clearly there was something wrong here. Murphy got wrong. And if we look at this code, there's an error return code of some, hexadecimal number. So what was that number? It is, well, at least the error message that when you go look up that return code is fairly straightforward. It tells us, go enable the debug layers and see what bad parameters you passed to the system so you can go actually check it. Now, the way you would enable debug layers, and the template that actually ships with Visual Studio does this for you now. On any debug builds, it will automatically check and see if the debug layers are already installed, and it will instantiate that way. So if I just go here, there's a section in the template that's it. When you're in debug, it has this function call, which I'm going to go to the definition. Oops. Definition, go to definition. There you go. And all this function does is create a null device, so it doesn't actually do anything. It tries to instantiate with the debug layers, and if it succeeds, then you know the debug layers on the system, and you will have it. The template will use it. And if it's not there, then it will fall back and not have the debug layers. So your application continues running. One of the behaviors of the D3D runtime is when you ask for a debug layer and the debug layers aren't on the system, most of the time the device creation fails. So with this template, it actually has a fallback to continue on. All right, so this template enables it. So let's see what the message was. Oh, here it is. So we have that message, which basically says, create swap chain for core window. Core window swap chains only support the DXGI swap effect, flip sequential swap effect. All right, let's go. Let's go find that. DXGI swap effect. Oops. Except I need to look in, not there. Swap effect. Current document, not in current document, entire project. And there we are. So what do we have? DXGI swap effect. We can see. So one of the things I told Murphy to do is every code change he makes, I wanted him to put it in ifdefs because I wanted to actually go review his code changes to make sure it was correct. And here's a mistake it looks like he made. And Murphy put in the comment, I was reading this great book on the plane last night. It said always use discard because it's the most efficient. Well, not exactly. You have to use swap effect discard, or you have to use the other swap effect, that the flip sequential, because what that lets you do is with a store app, you have composition happening, and there's a desktop composition manager that's actually managing, how things show up on the screen. In the case where your entire D3D content fills the whole screen, the desktop composition manager wants to get out of the way and just flip your back buffer right to the screen to get you the most efficiency, and that's what this does. So I'm just going to change that and put that back this way, and we will recompile. Oops. Recompile. And let's see how much farther. Oh, okay, so the application sort of is running. Ooh, okay, another problem. What is going on? Let's break. It seemed to have broken somewhere random. Any output? Oh yeah. So D3D11, this is again, the debug layers has caught this for me, and it's saying there's 2 threads were found to be executing functions associated with the same device context at the same time. This will cause corruption of memory. Appropriate thread synchronization needs to occur, and blah, blah, blah. Right. If I didn't have the debug layers installed, I program crashed somewhere randomly, and I'm not sure why. Right. This is sort of the type of detection it does for us. Now, the reason this is happening is in D3D, there's multiple sort of objects that you deal with. There's the device, which is fully multi-thread safe. You can access it for multiple threads. And then there's the context, which you use to render with. It has a bunch of APIs that it basically defines the 3D pipeline you're going to be working with. And that is single-threaded by default. There are options to make it multi-threaded, but if you do that, you're going to have slightly less performance, and it's usually easier to just do all your rendering on one thread and have any other calculations happen sort of in the background. So what did Murphy do here in this one? Let's go do a quick search. We're going to go look for rendering the maze, and what has happened here. There's the maze. Oh, okay, I see. Murphy was here. He said, CPUs today have at least 4 cores anyway nowadays, so let's take advantage, and why not do everything on other threads? Well, you can't really do that, right? And what he's done is he's taken rendering the maze. It looks like he's taken rendering the marble and put them, created tasks and just spawned off another thread to execute them. Well, I'm going to undo that change as well. Make those go away. Oh, by the way, when I publish this demo at later on after build, I'll be producing both the fixed version and the non-fixed version. There's actually about 26 errors in this program. So if I have a feeling that people will be using it sort of like a hiring test, if you find somebody who can find like 20 of them in an hour, just hire them on the spot. If they don't find like at least half of them, maybe you can train them, but it's hard to tell. So, okay, I removed those two. Stop that, rebuild. And hopefully those are the only two places. Yeah, okay, it's not crashing. Now, the flashing is annoying, and what that is again another feature of the debug runtime or debug layer. It's basically taking my resources as I create them and putting some random color in it, right? It'd be very easy to initialize those things to black, and I'd never notice that there's a problem here, right? But I have uninitialized resources that are just being used and being flipped. And actually, in this case, it looks like it's the swap chain that's actually having that problem. So let's go back and see what he did there. So there should be a call to clear render target somewhere. Yep. Again, Murphy got confused because he's thinking of WinRT classes, and these are actually C++ native objects. And he thought, oh, this is going to be 0 anyway. I don't need to initialize it. Well, no, you actually do need to initialize it. And in this case, I will turn that off as well. Put it back the way it should be. And in this case, we're going to create it as black, and we're going to get the render target and just clear that color. So we can stop that, and that should fix that flashing problem. Okay, that looks a little better, except see there's still a problem. We're missing the marble. Remember, there used to be a marble in the Windows 8 sample. Okay, we're going to go use the Visual Studio debugging to fix that one. But before I do that, I'm going to do something I'm going to do at several stages throughout the development process. Because while this isn't as much of a problem today as it used to be, because we all, when you're doing C++ DX programming, you're going to use COM pointers, and these smart pointers will deal with memory management. But it's fairly easy to forget and use a temporary variable, and some ref count gets incremented, and you wind up leaking memory. And in a lot of cases, leaking memory for normal programming won't really be as big a disaster as it could be with graphics. But graphics resources are so big. You have these large textures, you have these surfaces. If you are using the snap view or using two applications on the same screen and resizing one of them, every time you resize the application, you're going to recreate the swap chain. You may be recreating resources. And if you haven't gotten all the ref counting correct, or you're not using smart pointers, you're going to leak memory. So I'm going to go back before I do anything else, and we're going to look at that. What I did, let's go back here. What I did in this application, I go to the app. Now, if I was writing a desktop application, the D3D runtime would make this very simple, because on exit, it would immediately give me a big dump of, here's all the resources you forgot to release. So if I ever wanted to just test this on a desktop application, I get a list of things that are being leaked. A store app, I don't actually have control a lot of times of when it goes away, and you won't get a debug output. What will happen is it'll just disappear. It's very quiet, nice. The system will decide that, hey, you're using too much memory, you need to go away because we want the system to be responsive. So what I did was added this code at the end called dump D3D debug. And I've hooked this up to the F4 function. So when I hit F4, what's going to happen is this code runs. It will get a debug interface, which, by the way, you won't be able to do until after we ship 8.1, because I found that getting at this interface is currently an API that not available in a Windows Store app. So I'm cheating a little bit for this purpose of this demo. But we fixed this for the version or the internal versions after build. So you'll be able to do this once we release. But what you do is you get this debug interface, and on that debug interface, you can ask for, give me a dump of all the things that haven't been released. Now, before I do that, though, I want to clean up. So I clear the state and the context, because I want to make sure that objects that have been used and are in the process of going away, that they go away. I flush the pipeline, make sure that everything's committed, and then I release the main class, which is all my game logic, and I release the device resources, which is all things like the device, the swap chain, and so on. And by releasing them, they get destroyed, they go away, and then I dump the information. So let me go back, and I'm going to hit F4. Oops. Hit F4. And so the app has gone away. It has exited. And when I look here, there we go. You can see all the objects that I'm leaking currently. Now, that's not good. There's a bunch there. And it may at first look, a little bit overwhelming because there's so much stuff. Well, the thing about D3D is you have references between one object to another. So just leaking one object may cause you to have a whole bunch of objects to stick around. And it's fairly simple to figure out which ones they are because we look and see, okay, see all these objects have ref count as 0. Clearly, I don't have to worry about those because those are going away. Some of them will have an internal ref count of 1. That means the D3D runtime itself is still hanging on to them, and that's not really something I need to worry about. Also, you'll see that there's names associated with some of these. So like this one here, D3D device in line 222 of the program. That's actually something I've added. That's what I call an annotation on the application. And it's just a string that I've defined, and I've set it on the object when I created it. It's actually really lightweight. You can do this even in your retail code so that at later time when you have a problem in the field, you can actually take these tools, get these sort of dumps in the field without actually having to recompile your application as a debug application. Now, I could have named these things whatever I wanted. I could call them George or Henry or Fred, but it's device. And I also put the line number in there so that when I go and try and figure out where it is that I created this, I can go find that line. Now, when I look through this, actually, I'm going to make that. When I look through this, there's really two things. Looks like DXGI factory on line 431. And the swap chain are the two that really look suspicious out of this count. So let's go fix those. Okay, so that's in device resource. I happen to know where I create all these things or which file they're created in. And so I'll just go to the line number that I put in the debug information, 414. And okay, Murphy was here, and oh, okay, he's just using a pointer, not a smart pointer. And so what happens is this get function, which is getting the DXGI factory object, winds up incrementing the ref count on that object, and when there's nothing to release it, there's no code here to release it. The code he should have had was using a com pointer, which would automatically, as soon as it goes out of scope, decrement the ref count, and I wouldn't be leaking. So let's go fix that one. Oops. And then the other one was the swap chain, which was somewhere around 462, if I remember. Yeah, same sort of problem. He's just using a normal pointer, not a smart pointer. And in this case, okay, we'll make that go away. In this case, what he could have actually done, rather than doing that, is the class member itself has a smart pointer already, and we could have just passed that in rather than using the temporary. Temporary variables, it's fairly easy to make these sort of mistakes. So now, if I just stop debugging, rebuild this application, and I'll do my F4 again to have the system exit. Let's see what we have. And it looks nice and clean. There's no debug information from the D3D runtime. And so you do this several times during your development process just to make sure you keep clean. You want to keep clean on memory. You want to keep clean on any sort of error messages. If D3D is complaining about something, you're abusing something in the spec. It may actually work, which is the funny thing, right? Because the graphics drivers may have seen this problem so many times, they've worked around it. The D3D runtime, when it's not validating, it may actually happen to work in that case. You go put that app on a different device or, in some other different situation, and all of a sudden it stops working. So you have to keep a close eye on those things. So Okay. The other thing I'm going to show at this point, before I go and try and debug that problem, is the actually I don't need that one anymore. Is the DX control panel. Now, if you're like me, I like to have a lot of different SDKs on my system, and I've actually installed the June 2010 SDK on this system because I'm going to show you a demo shortly using one of the older samples from 2010. When you do a search on the start screen for the DX SDK and you have the June 2010 SDK, you get the wrong control panel coming up. And you'll be scratching your head on why doesn't anything happen? Well, you want the one in System 32, not the one that comes with the June 2010 SDK, which is this one. And you can tell that it's the new one because there aren't a whole bunch of tabs on it. So if you see a lot of tabs, you have the wrong one. And what this thing does is lets me control what the debug layers do. I can make certain messages go away. If I'm really abusing the API really badly, I can pick only the critical ones up front so I can fix those quickly. I can have it actually break on certain kinds of errors and deal with that. I can either force the debug layers to be always on. So if I don't want to do it programmatically in my application, like let's say I shipped it as a release application already, right? So it's not debug. It doesn't have a fallback. It's not going to add the necessary flag to create the device as a debug device. I can force it on through this control panel. And the other thing I can do, which is the really useful thing, is I can actually set the feature level I want to run at. So up until now, I've had it set to, feature level up to 11.1. And since this device is an Ivy Bridge, I think it's, I believe that's DX11, I'm going to get a DX11 device when my application creates its device, and which has a certain set of features that the hardware will support. If I go in here into the control panel and change that to 9.1, what I'm telling the runtime in the debug layer to do is limit the device I can create to 9.1. Don't use the 11 features because I want to make sure my app still runs at that lower feature set. Okay, let's apply that and see what happens. So stop. And we get a breakpoint. So what has happened is I have set this breakpoint in the code because this is the fallback path in my code. Here's the create device, and this should have succeeded. If my application actually set up the device correctly for working with 9.1, this should have succeeded. But what's happened is it's failed, and the template that actually ships with Visual Studio has this fallback to the software warp device. Because there's nothing worse than having an application that just crashes and you don't know why, right? This will always run because Warp supports all those feature levels. So even on a device that's like 9.1, I can still run all the 11 features, but it'll be running in software. Now, it's good from a user point of view, good from an application point of view. It's on a mobile device, it may be bad from a power point of view because I'm now using CPU to do all that work. But at least, the application can make forward progress. So why have I fallen back to this point? Well, if I go back up here where I'm creating feature levels, you can see that the list of feature levels I passed to the create device is only 10 and above. And Murphy's saying, why do I want to deal with DX9 stuff anymore, or DX9 class hardware? Well, unfortunately, a lot of the mobile devices are still DX9 class hardware. The Surface RT was a 9.1 device. And you need to test for that explicitly. So in this case, I will change this. And now I'm going to ask for all the feature levels. Now, I don't need to, this pattern that I'm using here, you don't need to do this way. Like, at the very least, you need to support 9.1. You should pick, feature levels that make sense. You're probably not going to have special code for each one of these levels. So if you do 9.1, maybe do 10, maybe do 11. If you're using the tiled resources feature that Matt Sandy was demonstrating yesterday, you'll definitely want to do 11.1 level. So when I do this, now my application runs, and it's running at 9.1 because the runtime has forced it to 9.1. It hasn't fallen back to warp rasterizer. You'll also note you'll also see when you fall back to warp that on the lower end devices that are running on battery, the clocks are typically pulled back down to a lower clock rate because they're running on battery. And so you may actually notice that the screen is a little less performant. In this case, because I'm running on hardware, it's going to be quite nice. All right. So we finished that, and I want to remember to go in here and put this back to 11 because I keep forgetting this, and I don't want to wind up doing the rest of the demo on 9.1 hardware. So let's do a quick recap. So what have we talked about? We've talked about the debug layers and the validation it does, memory leaks, the control panel, forcing feature levels, talked about some common bugs. Use the debug layers. Make sure your code is clean with it. Make sure you annotate your code. Set names on objects. I'll be showing some other annotations in the next section that will help you analyze your graphics. And be very careful with some of the advanced scenarios, like when you're doing multi-threading. Make sure that you do that properly. Those are the things you need to worry about when you're first creating. So now let's go look at the Visual Studio graphics debugging feature. And this feature we've been working on with the Visual Studio folks, and it actually existed in Visual Studio 2012, which is what I have here. This is Visual Studio 2012. Just make sure I got the right one because I have like several instances open. And I'm going to, graphics debugging is here under debug, graphics. I'm going to start diagnostic. I'm using this sample from the June 2010 SDK because we sort of used it as a stress test for making sure that we haven't broken anything while we were working on this example. And it has an interesting effect. So what we have here is a tank with a squid in it. There's some lighting. The sample itself will do multi-threaded rendering, which I'm not actually going to do here. But the sample itself is a fairly good stress test. So what you'll see in the background here is I have this new tab open called VS Graphics Debugging. And if I just do a print screen, what the tool will do is actually capture every single graphics call I make, put it into a list for me, and then show me a thumbnail, and I can actually walk through and look at the parameters that were passed to those graphics calls. So let's do print screen. Right. There we go. So it's capturing. But I'm actually running short on time, so I'm going to let that run for a second, and I'm going to switch to the template because I want to just show you what it would look like. Here's the template that ships with Visual Studio. It draws a cube. I've captured 4 screen captures at the bottom. And you can see the calls here. And remember that the D3D debug layers produce put random colors into each of the objects I create? That's what we're seeing here. As I click on each one of these, I'm seeing what color is being inserted into that random object at the time. And so there's a bunch of clears. I set a viewport, I set a render target, I clear the render target. Basically, these first few calls, I'm setting up the graphics pipeline. I set a vertex buffer that has the vertices for that cube. I set an index buffer that defines it. There's a set permitted topology, which tells me that the index buffer that I've just passed use a triangle list and tells the D3 runtime how to deal with it. There's a layout object, and eventually there's a draw. And that draw, just draws the cube. Isn't 3D simple? A couple of calls and a draw, and you're done. In fact, this application, takes 16 graphics calls to draw that cube, yet there's actually 56 graphics calls for this whole frame. Well, if I go down to the last call, you may not see this, but at the bottom right-hand side of the screen, there's 4 characters that say 60 FPS, or 5 characters. All these calls between here and line call 16 are all text calls. They're using D2D, which is on top of D3D. and it's just drawing those 5 characters. I have a great respect for our text folks because text is hard. I'd rather stick with D3D and just do 3D sort of program. That's sort of what the event list. Oh, perfect timing. It just finished. I actually managed to capture the application for multi-threading, and it finished in about the time it took me to do the presentation with the sample app. So why did I show you this? Well, let's go see what this looks like now after a year worth of working with Visual Studio folks in Visual Studio 2013. So this is, just make sure, Visual Studio Preview 2013. We'll do the exact same thing. We'll start diagnostics. So the functionality between 2013 and 2012 is the same. And this is the identical executable, the exact same project. I've opened them up in both of them. And let's just do, I'll move it over so you can see. We'll just do a capture. It's capturing. And it's finished capturing the APIs. It's drawn the thumbnail. So an operation that in 2012 took 2.5 minutes took about 10 seconds. And really, this is just improvements we've made in how the underlying tools work in terms of capturing this and the performance benefit you're going to get, or improvement in your workflow. Like this application itself, I'm going to turn it off. If you look at the event list, has 48,237 graphics calls for that one frame. That's actually not unique. We typically, and like there actually isn't that many draw calls in there because there's a lot of setup. And in fact, this sample uses the sample framework that was in the June 2010 SDK, and it does a lot of redundant graphics calls as well. You know, you could probably optimize some of those out. But if we only look at the draw calls, you know, we can filter out and look at the draw calls. Our goal when we look at tools is we'd like to be able to deal, in the tools at least, with 100,000 draw calls per frame. Now, you're not going to see a lot of that because even like the most advanced games today, 100,000 draw calls would be a lot of work on the GPU, and there's a lot of data that would have to flow to the GPU across the PCI bus to enable this. But we want to make sure that our tools are built that they're industrial strength enough to deal with that sort of volume. All right. So now that I've shown you this, let's use this to go debug this sample. And let's find out why our marble isn't showing up. Oh, let's just make sure it's built. Now, you may notice at the very top left-hand side, there's a frame counter. Visual Studio is actually drawing that as part of the tool. It's telling us what frame we're on. It's telling us how many captures we've done, just to make sure that you can tell whether you've actually captured something. So I'm going to turn off the pause. The app is running. There's no marble there. Do a capture. We've captured the frame. I'm actually going to capture 2 just so that I have 2 frames. Come back here. And let's turn it off. So there's our marble. And you can see this application, it draws about 286 graphics calls per frame. But there's a new thing here. There's a render maze and a render marble. What this is I've injected in the application itself these begin event, end events that encapsulate a certain set of D3D calls. And I've named it. So there's render marble. And so in the tool, it'll show up. And I can actually just expand that and look, okay, when I'm rendering a maze, these are the calls that get made to render the maze. And these are the calls that are made to render the marble. So so the marble actually isn't a lot, right? There's a update sub-resource, which is a constant buffer being updated, setting some vertex buffer, index buffer, and then I do the draw, except there's nothing being drawn. So where is that? So let's take a look at the pipeline stage. So the pipeline stage is another view of what this particular method has done. And the first one here is the input assembler. This is actually the geometry that I'm actually passing into the graphics pipeline. And if I just double click on it, it'll bring up one of the Visual Studio tools for actually looking at the geometry. I can actually use this tool for editing geometry and doing a bunch of other stuff. But it lets me go look at, is my geometry correct? Well, clearly this isn't, it looks right. So it's not the marble itself that's wrong. I haven't made it a point or something so that it makes it disappear. So that looks good. The next stage is the vertex shader. And if I click on the vertex shader, it brings up the HLSL, the high-level shader language code. And I can actually look through that and see, okay, that looks reasonable. You'll notice this little triangle here. What this little triangle lets me do is actually run that shader code. Remember, I've captured this big log of all the graphics calls. By clicking on that triangle, now what it does is it uses Warp. It runs that shader for that particular draw call. And it may look like I'm actually debugging because you notice I have the little yellow line. But what's actually happening is this is all captured trace of the shader running, and I can actually walk through this and single step through my shader to see how the shader executes and see if there's an error in my shader. I can do the typical sort of things you'd expect, is like mouse over things and see how the calculations, what values are getting into them. I can actually even go back up here higher and look at, okay, what are the things in the constant buffer that I actually pass to this shader? And in this case, I'm going to look at the model view, which has a 3D or a 4x4 matrix that is used to transform every point that makes up that marble into its two-dimensional space on the screen. Now, I've looked at matrices for a long time now on this thing, and I can tell there's something wrong with this one. Because the bottom row 3 there, should be all zeros with a 1 at the end, and it's not. It has this 45, 43, 42, and then the column on the right-hand side is all zeros, and it should have something. Because when I take my marble from model space to world space, I'm doing at most a scale, a rotation, and a translation. Well, the top 3x3 matrix that's making this 4x4 matrix is the rotation. The column on the right-hand side defines the translation, and a scale factor is multiplied through there. There should never be anything on the bottom one. So I think I know what happened here. When I did that conversion from basic math to DirectX math, I didn't take into account that basic math used column major ordering of the matrices. DirectX math uses row major ordering because it works better with SSE. And DirectX math is all about making the fastest code possible. So clearly I've done something wrong that got this matrix. And actually this matrix simply looks like it's flipped across the diagonal. Right? Actually, if I flipped it the other way so that that column on the one side became the row on the bottom, it probably looks about right. So it's probably a transposition error. Okay. Oops. Let me just catch up in my script to make sure I know where I am. So go back. Let's go look up, update constant buffers. And here's the code where I actually update the constant buffer. Now, the constant buffer is a set of data that's passed the shader that the shader uses to do its arithmetic. And it'll have things like the projection matrix in there. It has the model view transform matrix, or may have some other values in there. And in this case, as you can see, I converted this to DirectX math, and I'm loading the model matrix with an identity matrix at the beginning. I apply the translation in a certain direction to put into world space. I then multiply it by the rotation I want to be applying to the matrix. But I haven't done a transpose before I write it back into that constant buffer. What the code should have looked like is have this, multiply, then transpose, so that I go from the row major to the column major. And so let's fix that. So stop. I hopefully didn't change my HLSL code while I did that. Yes, I did. Where is... Something has to go wrong in every demo. Compile. And there's our marble. Awesome, right? It doesn't look like the previous demo, does it? The marble's the wrong color. But at least it showed up, so I got that problem corrected. So let's go back, and we will continue to use graphics debugging now. And let's figure out why it's not the right color. So start diagnostics. I have it running. Do a print screen, do a capture. I can stop the application at this point. And, okay, I don't need that. Make this a little smaller. There's a couple things I can use at this point. Actually, before I even go there, let's just make sure, is my texture correct? Maybe my texture is wrong, right? So if I go to the Solution Explorer and quickly go down here into the media textures, and there's a marble, there's a DDS file, which is a direct draw surface that's used by Direct3D. This is what I should have on the screen, and I clearly don't have that. But the actual DDS file looks like it's correct, so it's clear I didn't break the actual file itself. So let's close that one and close this. So there's a number of ways I can approach this problem. One of them is there's this tool called Pixel History, which when I click on any point on the screen, what it'll tell me is all the calls that went into generating the color that's at that point. So there's the clear context that happened, there's the draw call, which was used to draw the maze, and then there's a draw call that was made to draw the marble itself. So let's take a look at that. And, oh, okay, so I'm going to look at the actual pipeline stage itself, because there's the input assembler, which tells me, okay, these are the values, the resources are being sent to the graphics card for that pipeline stage. I can look at what's being passed to the vertex shader. I don't have a hull or a domain or a geometry shader for this sample. The pixel shader itself, oh, here's some interesting things. Let's look at these. There's some resources that are bound to the shader, and there's the first resource that's bound, which looks like the thing that the marble is textured in. And what's the other one? There's the right one. So I'm actually binding the right texture to my pixel shader. It's just it's not using it. So let's go figure out why that's happening. If I go back to my graphics debugging here, and we will bring up the event list. There's the call. One of the things I can do here is I can actually go and look at the event call stack. And for that draw call, I can actually now go and walk through each of the calls up the call stack that led to that draw. There's the draw itself. There's the function that called the draw. And simply walk through until I see something suspicious. Oops. Which looks like about there. Render. There. So there's this call to render mesh. What does it take as parameters? It has a context, which is the first parameter, a diffuse slot, which, okay, it looks like it's slot 1. And if you remember in our graphics pipeline we were just looking at, 1 was where the actual marble texture went. And really, the shader is supposed to be using 0. So somewhere along the way, this should have been actually a 0 rather than a 1. And so what I'll do is I'll just change that back to the correct value. And save that. Now if I run it and rebuild the application, hey, and we're back to where we are. This looks very much like the previous sample. We had a Win8, except now it's been all converted to Windows 8.1. It's using the right, API calls and so on. And we're ready to ship it, right? Well, before I do that, let me just quickly go back. Stop this. Let's just quickly do a recap. So, things I demoed in this one. The things that are new in the Visual Studio Graphics debugging is, first of all, it works for a lot more applications than the 2012 version did. We also added with the Visual Studio folks support for ARM debugging, so you can actually debug a Windows Surface RT with this tool now. It's very easy. We don't have it in the preview build, but by the RTM release, you will have being able to capture and play back on different actual hardware. Like what will happen is we'll actually fall back to warp and be able to play back something that your hardware doesn't actually even support, and actually do this sort of graphics debugging. So you can actually have somebody out in the field do a capture, send you that trace, so you don't actually even need the code. You now have a perfect repro. One of the things we use this for is we actually take traces and we run those traces over and over again to see when we, as Microsoft, make changes to the API and wind up breaking, some behavior. Because we can actually run the trace, check the output, and if the output's wrong, we know we've done something to change behavior in the way the APIs behave. And the other thing that's changed is this tool is now available also in Visual Studio 2013 Express. So you can actually use the Express edition, not just the Pro edition, which is what I'm using in this particular case. Okay, so the last topic, and I'm going to be fairly brief about this because I only have 2 minutes left, is validating your application. And there's sort of 2 classes of problem you're going to hit with validating your application. One is hardware differences. Right? We have the different features levels we already talked about, but there's also spec differences between the hardware levels. For example, DX9 hardware, for example, the output blender will actually do the blending without converting the gamma values to a linear value and blending it. DX10 class hardware actually converts to linear space, does the blend, and then converts it back to gamma. So the effect you'll have is when you're working on a machine like this, your picture looks beautiful, it's the right colors, everything's great. You put it on a DX9 class hardware, and all of a sudden the image looks darker, right? Because the combination was, the gamma operation was being done in the wrong color space. So there's a bunch of different things like that you'll notice with hardware. There's that one. There's normal maps. If you're using normal maps, you may have to bias them differently on DX9 class hardware that you'll have to worry about, and so on. There's also, I mentioned it earlier, and I'm not going to demo because I'm running out of time, but you can use the DX control panel to force warp on and then set feature levels and actually make sure that you're testing each and every specific thing. Because there's 2 ways sort of handling this validation. Either you can go out and buy one of every device out there in the world and test on each one, which, that's just too much. It costs too much. It's too hard. And you don't need to. In most cases, for testing the feature levels, you can use warp. For testing various other scenarios, you can use warp. The places where you need hardware is really only where there's real hardware differences, things like the gamma. And so if you have a RT device, like the Surface, and you have like a DX10 class device, that's probably plenty. But the other thing you can do for some of the other cases, and I'll just show a quick thing on that, is we do have this simulator as well. So now that the app is running, if I run it under the simulator, it'll actually start up a virtual machine. It'll start up my application. And you can see that the app isn't dealing with a rotated screen very correctly. There's a couple of things you want to be able to test. Rotation, DPI, screen sizes. You can do all that with the simulator. You don't actually need to buy hardware. Yeah, that looks terrible. So for example, in here I have the ability to set, what size of screen, what DPI. You should test at 100%, 180%. Make sure your app works. I know this app works. I'm not going to worry about that. But this is clearly wrong. And the new template that's in Visual Studio that I've built this application off of actually deals with all this rotation automatically. So clearly I've forgotten to apply some rotation matrix into my projection matrix when I did this. This is where I would have liked to restructure this code a little better, because while the underlying framework, the template I have, gives me that information, it was actually hard to get it into the sample. Let me just show you very quickly. Control H. So if I take all of these and change that to a no, there were still 15 places in the code I actually had to go modify to add in those rotation matrices to make sure this worked correctly. And that's purely because I had to pass down the matrix to lower levels because of the structure of this particular application I have. And so now when I run it under the simulator, after making those 15 more changes, and like I say, I will give you the broken sample so you can have fun trying to find all these yourself. It's a lot of fun looking for them. It's all correct. And actually, the other thing that's fun about this sample is the application itself has a particular view of which way X, Y, and Z face, which is not quite the same as the template code that I'm using underneath, which has X and Z in the same direction, but Y in the other one. So when I first fixed one of the problems, I found that my physics was going backwards, and so the ball was rolling uphill rather than downhill. So a few interesting things. So stop that. I'll quickly recap. Key is testing a couple devices with true hardware differences, like get a DX9 class hardware and a DX10 at least class hardware. I list some of the various scenarios you want to test to make sure that those work. So what we covered today, the debug layers, annotating, do it. You can even leave it in your retail builds because the annotations are actually very cheap and they only come into effect when you actually run the tool against your code. So you can have it out in the field, capture traces, and have meaningful output from it. Use Visual Studio Graphics debugging. It simplifies looking at your graphics because it removes it from all the other logic that's in your app, and then test on the hardware devices. Now, the Visual Studio folks asked me to put up this slide. They're having a feedback session in room 254. If you have feedback on what you want to see in these tools, or what you want to see in Visual Studio, please drop by and give them your feedback. They would like to hear about that. And evaluation, I would love to have everybody give me your evaluation on, was this useful? Was this sort of talk something I should do next time? Again, it probably needs to be a much longer talk. I'm way over now. So with that, I'd like to thank everybody. There's other talks. The first few we've already had yesterday, but there's similar follow-on talks that are all in this track. I encourage you all to go to those. And with that, thank you very much and appreciate your time.